So let's get into our lesson about chemical bonding today. So we're going to look at, first of all, just really briefly, the three different types of chemical bonds in general chemistry that we learn about. It obviously gets more complicated than what we're going to get into, but just as an overview. And then the bulk of today, what we're going to really learn how to do is follow this model of chemical bonding called Lewis structures and drawing Lewis structures. Okay. So as I said, there are three types of chemical bonds. We're just going to go over real quickly. We'll go more in depth with two of the three.
You can do it!
The first one is the ionic bond, which we already learned a little bit about at the beginning of the course, where we said that metals typically form ionic compounds with nonmetals or polyatomic anions. So these are the type of chemical bonds that result from the electrostatic attraction of a cation for an anion. Okay, opposites attract. And we'll get into that later in this week, but for now, we just want to set that one aside because what we're going to focus on for the next few lessons mostly is
As if we care.
the covalent bond, okay? So we're going to spend a lot of time talking about covalent bonds in the next, few weeks, really, till the end of the course. And that's in part because most of the bonding that we see in the world is covalent bonding, and so we spend more time talking about models of that kind of bonding. But to begin, review what you should know already. Remember when we talked about molecular compounds from the periodic table, those were the ones that involved nonmetals and metalloids up in the upper right-hand corner of the periodic table. And we said that they're molecular compounds because they have only covalent bonds. And the covalent bond, we said at that time, was a bond that results from the sharing of a pair of electrons. And remember now that we know what valence electrons are, those are those electrons in the outer shell of an atom, we can kind of put that all together and define a covalent bond as this: a chemical bond resulting from the sharing of valence electrons.
Wait a minute!
Okay, and then the one we're just going to mention in this bullet, and that's it: metallic bonds. Those are unique in that, and the name kind of gives it away, they involve pure metals or metal alloys. So they are a chemical bond consisting of nuclei. Remember, nuclei, that's just a plural. Nuclei is just the plural for nucleus, okay? So the chemical bond consisting of the nuclei of metal atoms surrounded by a sea of shared electrons, okay? And that's about all we're going to say about metallic bonds. All right, so now what we're going to do is we're really going to focus on the covalent bond and describing its character. So in order to do that, I want to kind of diagram this out a little bit. If we were to look at potential energy versus distance between two nuclei, and we're going to do a very simple covalent bond, a covalent bond between two hydrogen atoms, all right? And so let's say that we have two hydrogen atoms out here and they're an infinite distance apart. So on the x-axis, we've got distance between the two nuclei, and then we're going to plot that versus potential energy here on the y-axis. So over here, what we're going to say is we've got two hydrogen atoms that are just really far apart. So, they're there. Each of those are hydrogens. Okay, but we're going to say that the distance between them is an infinite amount, all right? And so that means that they really don't recognize each other. So the potential energy, which remember that potential energy is energy associated with relative position. And so since those two nuclei are not influencing each other at all, then that energy we're going to call zero, okay? All right, so that's going to stay zero until we get to a point where those nuclei are close enough together. So there's a hydrogen atom. And so now they're approaching one another, okay? And so there's a certain distance between them. And so now what's going on is the electrons on this hydrogen atom are being attracted to the nucleus of that hydrogen atom, and the electrons on this hydrogen atom are being attracted to the nucleus on that hydrogen atom. And so that's an attractive force. And so that has a certain amount of energy that would be required to overcome that force. So the energy starts to drop, okay? It starts to slope down, okay? And so then what happens is it reaches some minimum, okay? And so at this minimum energy, that's when we kind of hit the sweet spot. That's when the two hydrogen atoms are in bonding position, okay? So now the distance between those two is where nature wants it to be. Just like if I were to put a ball right here, it would roll downhill until it got to this minimum, right? Well, it's the same thing here, but it's instead of gravity working on these two atoms, it's that electrostatic force. It's that opposites attract force that's working on them. Okay, so right there is that minimum energy, okay? So what we could say then is that energy on the y-axis here, that would be the bond energy. Okay, that's the bond energy of this H2 molecule. So that's the energy that I would have to put in. If I wanted to break that bond, I would have to put in that much energy. Okay, that's how much energy would be required for me to pull those two hydrogen atoms apart. Okay, and the other thing I'll point out is right there, that represents a certain distance. Okay, so that's the bond length. The bond length. Okay, so that bond length, if I were to, put this hydrogen molecule under the right microscope, so to speak. Of course, it's not a microscope; it's other instruments that are used. But and I were to measure that length between the two hydrogen nuclei, that's the length that I would measure. And of course, it's an average because these two hydrogen atoms are kind of vibrating back and forth; they're oscillating. But that average distance between the two is what we would call the bond length at that minimum energy. Now, if I were to be able to kind of put those two atoms in a clamp and kind of squeeze them together, push them even closer together, then I would move out of this sweet spot and I would really start very quickly increasing the energy to a positive. So a repulsive, down here is negative because it's attractive, but up here is positive because it's repulsive. And that's because if I get too close, then the positive charge on this hydrogen nucleus begins to feel the repulsive force of the positive charge on that hydrogen nucleus. And so, nature doesn't want that. So it really starts to increase that energy to an unfavorable kind of level. All right. So this is what you could do to just to understand why a hydrogen bond forms, or any other covalent bond forms, because at a certain distance they really don't. Each atom really doesn't know that the other one is there. But as they approach each other, the electrons on one atom starts to feel the attractive force of the nucleus on the other atom, and so that leads to a decrease in energy, and it reaches some minimum, okay, some spot at which really that's where you form the bond. So at this point, this minimum, you've formed that covalent bond. And so the electrons are not only orbiting this nucleus, but they're also orbiting this nucleus. And its electrons are not only orbiting this nucleus, but they're orbiting this nucleus. And we'll get into that more later in the weekend and next week when we talk about hybrid orbitals and molecular orbital theory. Okay, but if I go a little too far, I push those two positively charged nuclei together a little closer, then that's destabilizing and it really pushes the energy up. Okay, all right, so let me erase that. Go back to arrow. And this is just a lot prettier. Okay, same kind of information I just drew out for you on the previous slide. The one thing I will point out though is that the units for energy used in this picture are different. I used electron volts, which is typically the units of energy that you will use on the atomic scale, just like we use atomic mass units as the typical unit of mass at the atomic scale. Electron volts are typically the units of energy used at the atomic scale. But this picture, this graph uses different units. It uses kilojoules per mole, but it has the same shape. It has the same features, okay? It's just that this would be the energy that would be required to break 1 mole of hydrogen-hydrogen bonds, not just the energy of 1 hydrogen-hydrogen bond, okay? But the bond length would be the same. All right, so hopefully that makes sense. So now we're going to get a little bit further into what's known as Lewis theory. This is going to be the first of several models of chemical bonding that we're going to look at. We're going to look at Lewis theory, we're going to look at valence bond theory, and we're going to look at molecular orbital theory. And each of them have sort of unique strengths, but they also have weaknesses. And so let's just get into it. So, this is named after somebody. It's named after Gilbert Lewis, who in 1916 developed this. So what he did was he just proposed that atoms are going to share electrons. Why? So they can get that electron configuration of a noble gas. We learned that last week, okay? Things tend to lose or gain or share electrons so that they get that electron configuration of a noble gas. And that leads to something we call the octet rule, because that number that they're looking for often is 8, particularly if it's a main group element near the top of the periodic table. Things like carbon and nitrogen and oxygen and hydrogen. Well, pardon me, not hydrogen, but all those elements that are near the top of the periodic table typically want 8 electrons in their valence shell. So we call that the octet rule. So here it is. Atoms tend to lose, gain, or share electrons to obtain a set of 8 valence electrons. And remember what that looks like in terms of electron configuration. The N is the principal quantum number, S is the orbital type, you can think of it as the the letter that represents the L quantum number, and then the superscript is the number of electrons that are in that subshell. So like 1s2, or pardon me, 2s2, 2p6. That's a common one for following the octet rule. Okay, so as I said, this really just applies to the upper part of the periodic table. Once you get down to period 3 and below, then there's other things that you have to take into account. But you know, so many compounds that we deal with on a day-to-day basis are in periods 1 and 2 that it's very, very useful. The octet rule is often, you know, used to, if you have to take organic chemistry, you'll talk about it all the time. If you have to go into biochemistry, you talk about it all the time. So the octet rule, there it is. Okay, so the first thing we want to do with regard to Lewis structures is learn how to do Lewis symbols, or sometimes they're called Lewis dot structures, right? And we want to first of all apply those to given elements. So first of all, you just write the symbol for the element, and then you're going to put dots around it that represent the valence electrons. And so the Lewis symbol is a chemical symbol for an atom surrounded by one or more dots that represent the valence electrons, okay? So those dots are just arranged around the elemental symbol. And it looks something like this. Oh, well, pardon, some of the rules that we follow, and then we'll give you some examples. So the first 4 dots, or the first 4 electrons, you're going to write those as unpaired, and they're going to go on the top, each side, and the bottom, all right? And then if you have more than 4, then you add those to the lone dots to form up pairs. Okay, so the first 4 are going to be unpaired dots, but then if you have more than that, you start to pair up the dots with a partner. All right, so what am I talking about? Here's a couple examples. So first of all, carbon. Remember that carbon has 4 valence electrons. And so you can start anywhere. So let's say we start at the top. You draw a carbon, the symbol carbon, and then a dot at the top, dot on one side, dot on the bottom, a dot on the other side. Okay, well, what if we had more than 4 valence electrons, something like sulfur? Okay, so sulfur, just if you want to draw this out, you would, I'm just going to kind of circle them in the order that they would be put there. So sulfur would have the 1, and then the 2, and then the 3, and then the 4, and then 5 and 6. Okay, those are the 6 electrons, and how you would put them into the Lewis dot symbol or structure for sulfur. Okay, so you have them unpaired first, top, side, bottom, side. But then if you have more than that, you just start to pair them up like we did here and here. Okay, so let me just do another example just right here in this space. So nitrogen has 5 valence electrons. So 1, 2, 3, 4, and then the 5th one I would use to pair up right there. Okay, all right, so let me erase all that. Go back to my cursor. So this is a nice little diagram that shows you the Lewis symbols for all the various elements in the main group. Again, it gets more complicated with the transition elements, so you won't see that very often, but you can do that quite reliably with the main group elements. Everybody in group 1, group 2, and group 13 through 18, okay? So an important concept is the bonding capacity, and the way you can get that from the Lewis symbol is that it's the number of unpaired dots. So the number of unpaired dots is what you could call the bonding capacity. So for example, you know, beryllium here has I would say that it has a bonding capacity of 2 because it has 2 unpaired electrons. Nitrogen here has 1, 2, 3 unpaired electrons, so it has a bonding capacity of 3. That's what we're talking about. Okay. All right, so members of the main group elements, members of the same group, have the same number of valence electrons and therefore similar bonding capacities. I'm careful to use the word similar because what you're going to see later in the week is that it's not necessarily a set number. For many of these elements, it is fairly a set number, but for some of them, it gets a little bit more tricky. Okay, but first things first, you know, we build on what we know, right? Okay, so. Compounds, everything we talked about so far are just the Lewis dot structures or Lewis dot symbols for elements, but we can also do this with chemical compounds, okay? So first of all, some of the ways that we represent things. So if you have a bonding pair of electrons, remember we said that a covalent bond is a sharing of a pair of electrons. So how are we going to represent that? So it's a pair of electrons that are shared between two atoms in a covalent bond.
My name is Bond, James Bond.
Okay, well, there's different types of covalent bonds, as we will see later in the week. And one of them is a single bond, and that's where you have two atoms sharing a pair of electrons. They're sharing one pair of electrons. Okay, or you can think of it as two electrons. So a couple ways to represent that. You could represent that with two dots sort of sandwiched between the two atoms. Okay, so this is a hydrogen atom, and then the two dots represent that single bond. But more commonly, the way you will see it, and this is the way that I will do it, I don't draw my Lewis structures much like this. I tend to focus on using lines to represent single bonds. So if you have a single line between the two symbols, then that represents a single bond. That line right there represents these two electrons shared between these two atoms. Okay? So you can have instances where you have both. You have dots representing paired up electrons on an atom, and you can have lines representing shared electrons between two atoms. So water is a great example of that. And if you have a lone pair of electrons on an atom, then you will still see them represented as dots. So a water molecule, H2O, can be represented like this, right? Where you have the hydrogen, and these two dots next to this oxygen represents the single bond between this hydrogen and the oxygen. And then again, on the right, we have this hydrogen atom with the two dots sandwiched between it and the oxygen atom. So these two represent the single bond between this hydrogen and the oxygen. But then the oxygen also will have a lone pair of electrons, or actually has two lone pairs of electrons on it as well, okay? So it gets a little cluttered. So that's typically why I don't do it particularly with compounds. And so the way you most often see it represented is the hydrogen with a line connected to the oxygen to represent the hydrogen-oxygen single bond. Same thing over here. But then the new information in this particular part of the notes here, this bullet, is that you can and should also draw in the lone pair of electrons that are on the oxygen Lewis symbol, and you see those there, okay? So this is just, again, some of the conventions that are used when drawing Lewis structures. Okay, so there are some step-by-steps when drawing Lewis structures for compounds, and so I'm just going to go through those step-by-steps, and then we will do some examples, and I'll get you guys involved in this real soon. So the first thing you need to do is just determine the number of valence electrons that are in the structure as a whole. So NVE stands for number of valence electrons, okay? So what you do is you just add up, sum the valence electrons for all the atoms in a molecule. But if you don't have a molecule, say you have an ion, like a polyatomic ion, then what you do is you have to add or subtract electrons to account for that charge, to account for the ionic charge. So that's the first thing you do. So sum valence electrons for all atoms in a molecule, add / subtract electrons to account for ionic charges. Okay, the second rule is that you're just going to arrange the atoms in a pattern that shows how they are bonded. Well, you may be thinking, well, how do I know what pattern they are arranged? Well, here's a couple hints to help you out with that. So first of all, you have to pick an atom that's going to go in the middle, and then the other atoms are going to go around it. So the atom with the largest bonding capacity, and remember that has to do with the number of unpaired electrons that it has, you're going to put that one in the center. Well, then you're going to arrange the other atoms around the center. Okay, and you're always going to put hydrogen on the periphery. Okay, because remember, hydrogen only has one, the bonding capacity of one. So you never have hydrogen in the middle unless it's just a weird kind of molecule. Okay, so you put the atom with the largest bonding capacity in the middle, and then you put the other atoms around it because they have a lower bonding capacity.
My name is Bond, James Bond.
Okay, so then you just start connecting things. You connect the atoms on the periphery with the atom in the middle with single bonds. And you understand that that's going to take away from essentially what you're doing is you're assigning electrons to places. And so when you connect those atoms with single bonds, you're using up some of that total that you figured out in step one. Okay, step three, you're going to complete the octet. We said in previous slide that atoms like to have an octet of electrons in their valence shell. So make sure you do that. Complete the octet of atoms connected to the central atom by adding lone pairs, except for hydrogen, because hydrogen doesn't want an octet. Hydrogen's happy with two. Remember, hydrogen only has that one s orbital. So it's happy just to fill up that valence orbital, which requires only 2 electrons. Okay, so we don't put 8 electrons on hydrogen, just 2. Okay, so then what you do is you've reduced the number of valence electrons by doing all of this steps 2 and 3, making the bonds, but then completing the octets with lone pairs. So then you just compare that number with the number of valence electrons you figured out in step 1. Okay, so that can lead to 2 possibilities. First of all, if you've used up all of your electrons that you figured out in step 1, you're done. But if you are not done, if you still have some electrons left over to put somewhere, then the place that you put them is on the central atom. So if not, you place the remaining electrons around the central atom, even if it gives you more than 8 valence electrons. And we'll explain why that doesn't matter later. But you put them on the central atom if you've got some left over.
Making copies.
So then, after you've done that, you make sure that you've completed the octet around the central atom, okay? And this is something you won't necessarily have to do, but if you need to move electrons around to give the central atom an octet, what you do is you convert one or more lone pairs on an adjacent atom into a bonding pair on the central atom. All right, and I'll show you how to do that and the consequences of that in the examples. Okay, so those are the steps, and I know it's a lot of words at this point. You probably will really learn things by example, so we'll go ahead and launch into those examples. Okay, so here's an example using PCl3. So we're going to follow the steps. So first of all, we're going to calculate the number of valence electrons. Phosphorus has 5, right? I looked that up on the periodic table. So the 5 is for the phosphorus, based on its position in the periodic table. Within the chlorines, each have 7, but since there's 3, okay, so 3 times 7 is 21, plus 5 is 26, all right? So then the next thing to do is to pick out what the central atom is going to be. Well, I've got phosphorus and I've got chlorine to choose from. So, and another hint is if you've got a formula where you've got multiple of one type of atom, but only a single of a different type of atom, that's also the giveaway. That's the one that's going to go in the middle. But it also turns out that this follows the bonding capacity rules because phosphorus has a bonding capacity of 3. Phosphorus has the Lewis symbol that looks like this, okay? So it has 3 unpaired electrons, so it has a bonding capacity equal to 3. Whereas with chlorine, if you look at its Lewis symbol, it has only 1 unpaired electron, so its bonding capacity is equal to 1. So that's why I choose this, the phosphorus, as the central. And I'm going to put the chlorines, oops, that should be a Cl. I'm going to put the chlorines around it. Okay, so I put the phosphorus in the middle, and I put the chlorines around it. Okay, so that's step 2. So now the next thing that we're going to do is we're going to start using up some of these 26 electrons. And the first thing we're going to do is connect all those together with single bonds. Okay, and each one of those uses up 2 electrons. Okay, and there's 3 of them. So that's a total of 6 electrons that I've used up doing that. Okay, so now I have 20 electrons left over. Okay, because I used up 6 electrons with these 3 bonds. So if you're following the step-by-step, the next thing it says to do is to put lone pairs around these chlorines to make them have their octet. Okay, so start doing that. I'm going to do that for each one. Okay, so now every chlorine has an octet. By the way, these 2 electrons, you can assign them wherever, because remember they're shared. So those 2 electrons go with the chlorine when I'm counting electrons on the chlorine. So this chlorine has 2, 4, 6, 8. This chlorine has 2, 4, 6, 8. So they've got their octet now because I can, since these electrons are shared, I can count them as going with the chlorine. And when we get to the phosphorus, we'll count them as going with the phosphorus also. But okay, so all that, I did assign 9 more electrons there. So that's why I did that. Or pardon me, 9 more pairs. So 9 times 2 is 18. So I had 20, and I subtract the 18 that I just assigned when I put those lone pairs around the chlorines, and I have 2 electrons left over. So following the rules, it says that I need to put those on the central atom, the phosphorus. Okay, so I put the remaining 2 electrons on the phosphorus. Okay, and that really much tells me that I'm done because everybody has an octet now. So this phosphorus has 2, 4, 6, 8. These chlorines, we already established they have 8 electrons. And I've used up all of my electrons now. So, my 26, all of them have been used up. So we're done. Okay. So now actually what I want to do is I'm going to pause this. I'm going to show you how to do this in Chem 101 because the tool that they have for doing Lewis structures in Chem 101 is actually pretty cool. Okay, so now I want to talk about how you're going to use the Chem 101 app to do these Lewis structures. So you will always start with a screen like this. And it's pretty intuitive. You know, you may not need any sort of instruction on this at all, but I want to show you all the bells and whistles because it's very, very helpful. So the red means that that's the atom that you've selected. If I click on the bond, that means I've selected that bond, or if I click on another atom, then I'm selecting that atom. And you'll notice that over on the left, you've got a slider scale for the number of electrons that I want to put on that atom. And then the other thing I could do is I want to change the number of bonds that this atom is participating in, then I can use this slider bar. So it just, you know, determines the number of bonds that the selected atom is participating in. Okay, so I'll go back to this atom, and the first thing I want to do is define what that atom is. And so I can go to my periodic table, and I want this to be the phosphorus. Okay, and I want this phosphorus, I decided it was going to have bonds with 3 different chlorines. So those are my 3 chlorines, but I need to make them chlorine. So I select one, change it to chlorine, select the other, change it to chlorine, select the other, change it to chlorine, okay? And so now, with these, if you're following the steps, the next thing I want to do is I want to put the lone pairs of electrons on this chlorine. So I want to give it an octet, so I need 6 electrons for it to have an octet, 2, 4, 6, 8. So now I do that to all of my chlorines, give each of those 6, give each of those 6, okay? And so now, again, if you're following the step-by-steps, you've got 2 electrons left over, and it says to put those on the central atom. So I click the central atom, and I do that, okay? And so now if you want to see, if you want to make sure that you've got an octet on everybody, what's one of the nice things about this tool is you just click this little button right here where it says valence electrons, okay? And it tells you in a circle the number of valence electrons on every atom, okay? And if you ever get messed up, then you can always just undo something, or you can just reset it from the beginning, okay? Okay, so we're going to do another example here for NH4+. So this is one that is an example of an ion. So the unique things we do for ions. So first of all, we're going to follow step by step. So we just calculate the number of valence electrons. So 5 for the nitrogen, 1 for each hydrogen, and there's 4 hydrogens. But because I have a positive ion, I need to subtract 1, right? That's what positive means, like a deficiency of electrons. So I'm going to subtract 1. So we have a total of 8 electrons. So the next step is I need to pick a central atom. So once again, it's pretty obvious here. I've got 4 hydrogens and 1 nitrogen, so I'm going to pick nitrogen to go in the middle. But also nitrogen has a bonding capacity of 3. Hydrogen always goes on the periphery. So I'm going to put nitrogen in the middle, and I'm going to surround it with the 4 hydrogens, okay? And so now I'm going to just connect everybody. The next step says to connect all the peripheral atoms with the central atom. That's what those single bonds do. And so each one of those represents 2 electrons. So I subtract that from my total. So my total is 8, and I subtract from that 2, 4, 6, 8. So I've used up all of my electrons. I don't have to do anything else at that point. That is the Lewis structure, but it is a commonly shown, because it's an ion, there's a couple ways to do that. I could just put a positive, like a plus sign on the nitrogen, but you will also see it like this, where you have brackets around the whole thing and you put the positive charge there. Okay, so you see it both ways. You could see the positive charge as a superscript on brackets that kind of encases or encloses the whole Lewis structure, or you might also see the positive charge assigned to the atom that actually has the positive charge, that's called formal charge, and we'll get to that in another lesson as well. Okay, all right, so that's an example of an ion. Okay, so now how do we do multiple bonds, okay? So let's talk a little bit about what they are first, just in theory, and then we'll show you how to do it with the Lewis structure and also with the Chem 101 tool. So first of all, you can have single bonds, you can have double bonds, you can have triple bonds, and even out there in the known universe, there's a few examples of like quadruple bonds, but they're pretty rare. But you see, all the time we encounter compounds with double bonds and triple bonds. So a double bond,
Okay.
what that means is that you have 2 electron pairs that are shared by 2 atoms. Okay, so it's a total of 4 electrons shared in 2 bonds. Therefore, you have the name double bond. So 2 electron pairs shared by 2 atoms.
Take off, eh?
Okay, and it's represented with a double line, okay? So instead of a single line between 2 chemical symbols, elemental symbols, you'll see a double line between 2 symbols. So for example, oxygen, right? So that's one that is a, you know, a compound with a, it's not a compound, it's an elemental molecule that has a double bond.
Ah.
Okay, so those 2 oxygen atoms, by the way, this is what you're breathing in right now. So the oxygen that we're breathing in and using that's found in the atmosphere is in the form of O2, which has a double bond. So each oxygen shares that pair of electrons, shares that pair of electrons, and so we represent that with a double line. Okay, similarly, you could have a triple bond, which, you know, you probably guessed it by now. But that's where you have 3 electron pairs shared by 2 atoms. And so an example of that would be the nitrogen in the atmosphere. Okay? And it's represented with a triple line. So single line for single bond, double line for double bond, triple line for triple bond. Each one of those lines represents a pair of electrons that is shared. So nitrogen is like that.
I triple dog dare you!
So it has 3 electron pairs that are shared. And so this is another reason why I don't typically represent it like this, okay? Because it's not clear that all 6 of those electrons, or it's not clear how those 6 electrons are shared between the 2 nitrogen atoms, but this I think represents it better. All right, so you got the 3 lines representing the triple bond there. Okay, so now let's talk about how to draw a Lewis structure when it involves a multiple bond. So here's the formula, okay? 2 hydrogens, a carbon, and an oxygen. So first of all, we're just gonna follow the step-by-steps. So we calculate the total number of valence electrons, the NVE. So we've got 1 for each hydrogen, so 2 times 1. We've got 4 for the carbon, and we've got 6 for the oxygen, for a total of 12. So now I have to pick out which one of these is gonna go in the middle, all right? So this is where you have to take into account the bonding capacity. Because carbon, there's 1 carbon and there's 1 oxygen. So you can't go just based on the number of atoms of a specific type in the formula, because I've only got 1 carbon and I only have 1 oxygen. So it's a competition between the 2. Which one goes in the middle? Well, the one with the largest bonding capacity, which is carbon. Okay, so carbon goes in the middle and the other atoms just go around it. Okay, so I put the other atoms around the carbon. And so then I just assign or connect them with single bonds. That's the next thing I need to do. So I connected those atoms together with single bonds. So that used up 6 electrons. Okay, so 3 bonds, each 2 electrons. So I have 6 electrons left. So the next thing to do is to give the oxygen its octet. Remember, hydrogen, they're happy with just 2 electrons. I don't need to give hydrogens an octet. Okay, so each lone pair, or pardon me, each oxygen lone pair is going to use up 2 electrons, so I used up 6 more electrons. And so you might think you're done because all 12 of my original electrons have now been assigned somewhere. But make the next bullet, if you're following the step-by-step, says to make sure that your central atom also obeys the octet rule. Well, right now, this carbon is not obeying the octet rule. It only has 6 electrons, 2, 4, 6. Okay, so carbon does not have an octet. That's a problem because carbon wants an octet. So what do I do about that? How do and the thing is, I don't have any more electrons to give to the carbon to enable it to have an octet. Well, what's going to happen is that carbon says, hey, oxygen atom, I don't really have an octet yet. I'd like to have an octet. So you've got some lone pairs there. How about we share another pair of electrons so that we can both have an octet? And the oxygen says, yeah, sure, why not? I don't know why I have an elephant sound effect there, but anyway, I guess it kind of gets your attention. So the idea here is that one of these lone pairs on the oxygen is going to become another bonding pair between oxygen and carbon so that they both can have an octet. So we're going to convert a lone pair on the oxygen into a bonding pair between the carbon and the oxygen. All right, so now all of a sudden, transforms into a bonding pair, okay? And so this is the Lewis structure for this molecule. This is formaldehyde, by the way, for those of you who are biology majors and you go into the dissection lab, dissecting the worm or the frog or whatever, that smell that comes to mind when you have dissection lab, it's this compound right here, formaldehyde. Okay, so
You got it.
that forms a double bond, and that means we are done with that particular Lewis structure. So Okay, so now we are back at the CHEM0140 tool. I want to show you how to do multiple bonds with this. So we said the carbon's going to be in the middle. So right now I have this atom selected. So let's make that a carbon. Okay, and that carbon at first only had 3 bonds, right? That's just following kind of that. Using CHEM0101 doesn't totally get you away from just doing these with scratch paper, but following the steps that we would use on scratch paper, that's what I'm trying to mimic here, right? And so one of these was an oxygen atom, so I'll turn it into an oxygen. And the other guys were hydrogen, so I'll make them into hydrogen. Okay, all right. And so now remember what I did was I gave the oxygen its octet. So I select the oxygen and give it 3 lone pairs so that it has its octet. All right, but now I realize that carbon doesn't have its octet. So now what I can do is there's a couple ways you could do this. I think that the best way to do it is to click the bond and to make it into a double bond, okay? All right, but right now, what you need to do is also go back to the oxygen and bring that back down to 4 electrons. Okay, because when I converted that single bond into a double bond, I did that by changing one of those lone pairs into a bonding pair. And so you got to remember to go back and change that on the oxygen. And so right now, again, just to make sure everybody's happy, you can click the valence electrons button, and oxygen has 8, carbon has 8, the hydrogens are happy with 2. So everybody's good to go there. Okay.